Well, I thought, make sure you stay awake today. We'd start with this one. This is the most classic calculus cartoon. Let me find it. There it is. From the far side, conducted by an alien circus company. Professor Doyle is forced to perform calculus equations in center ring. There you go. Hope that doesn't wind up being me someday. That's your wake-up call today. And what we want to do first is finish our short topics so you have something to work on that's new this week. What's new this week is applications of second order equations, right? The exam is on second order equations tomorrow. Don't come to here unless you want to take your test here. You can take your test here. I'll show up, and if anybody wants to take it on paper here, but it's open book and open notes. You're welcome to take it home with your laptop. Just no help from many people. But we'll finish this material on applications of those second order equations today. And you can work on that, hopefully be ready on Monday, see if you have any questions then, all right? This will not be on the test, these applications out of chapter 3.3. I sent out the homework yesterday for this week. Hopefully you got it. That's what you do before next Monday. And we'll finish it today briefly and then ask whatever questions you want for the review for the test. I'm not usually here for an office hour after class on Wednesdays. I keep it before class on Wednesdays, but because there's a test, what I'll do is I'll go over to my office and sit there for at least half an hour and see if anybody shows up. If you show up at my same link as you get on for the video, right? My office hour. Just if you have questions after class, meet me online and I'll discuss them. If you show up more than half an hour afterwards, I may have left or I may still be doing questions with somebody who knows. And then tomorrow I'll come in earlier than usual. I'll come in at least by 9 o'clock. If you have some last minute questions, you can ask them before the test. All right. So if you have questions other times can't make those, send me an email. And if I get it in time, I'll reach you at other times too. So here's what we were doing last time. We said this is a classic differential equation that comes from the mass of a spring. Possibly with a dash pot damper attached that makes resistance proportional to velocity, which we said is not air friction for macroscopic objects like this moving at reasonable speeds. Any motion where there's turbulence, the air friction is normally proportional to velocity squared. But this is useful in things like cantilever beams and so forth. This damp is linear damping. So we'll say there's some sort of damper down here. And the spring has a Hooke's law constant K that says the force exerted by the spring tries to restore it to its equilibrium position at 0. With force proportional to the distance u that's displaced down. So this is the positive u axis downward. And it's out u, then the force is minus ku, right? Pull it twice as far, pull twice as hard. And that's a good approximation if you don't pull the spring too far. It's an idealized spring law. And then we might just attach something here, push it with our hand or put a rocket motor on here or something that gives it a push as a function of time, f of t. And so the interesting case is when you push it sinusoidally. So this would be your f of t here, or forcing term they sometimes call it, because I called this the f applied. Anyway, f of t, a function of time that you apply. It's called a forcing term, but because if you subtract these things over to the other side, then minus c du dt is the force due to damping. All right, minus ku is the force due to the spring, and this is any other applied force. this is a forcing term. It's equal to mass times acceleration if nothing else is there, and it's added to the other forces if other forces are there. So the interesting case we said is when this is sinusoidal, and this actually comes up normally in lots of electronics engineering situations. But it can also come up in vibrating systems, mechanical systems such as this. All right, so we had two cases then for the, we actually have four cases: the undamped, undriven motion, the damped driven motion, the undamped driven motion, and the damped driven motion. We had two cases, I should say, for the third case, the undamped driven mass. So within the third of the four cases, we can have no damping. This term is gone. C is 0. And this equation then, with a sinusoidal driving term, leads to this solution. Maybe I should put what the equation is. It's mu double prime plus ku equals A0 cosine omega 2t plus B0 sine omega 2t, which we can interpret as a single sine wave. Remember, trigonometry says you can rewrite this as a number times sine omega t plus B0. As long as these have the same angular frequency, you can combine them into a single sine wave. Just by the sum of sines formula for sine of the sum of angles formula from trigonometry. So this is pushing the system with a force that's sinusoidal like this. It just makes a sine wave. And you can rewrite it this way with A0 equals the root sum squared, little a0 squared plus little b0 squared. If you have this kind of a equation, we said there's exactly two cases. This case, what you have is a sine wave that's the homogeneous solution, plus another sine wave of the applied frequency omega 0. That's the particular solution, and your motion u is the sum of those two sine waves. Maybe here's one, and the other is just making a little wiggle like this. Then the sum of those two just kind of wiggles around this one, right? So your solution might look like this. If they're more the same size, then it doesn't look so easy, but that's the first case. But in the second case, what you have is a sine wave plus t times a sine wave. And we said this one is called resonance because the second term, you can consider the curves. If you rewrite this u particular as call it A0 hat. If I write this as a single sine wave, B0 sine omega 0 t plus P0. The particular solution, whatever it is by undetermined coefficients, is a sine wave like this. And then it has amplitude B0 multiplied by t. So this is now y equals B0t, this line. And this one could be y equals minus B0t, where B0 is the amplitude of this wave. And what you're doing is you're taking amplitude B0 times t, that's this line and this line, times the oscillation between plus and minus 1. So the particular solution goes like this, building up larger and larger oscillations, this linear function times the sine function. And then when you add it to this one, which is just a little, it's just a sine wave, what you get is something that eventually looks mostly like that one, right? It's just that one oscillating around this one. All right, so that's called resonance. If you push it at the same frequency that the system wants to naturally oscillate at, square root k over m. And maybe I better make it clear. I said omega. I mean, omega is square root of k over m, the original system. So omega or square root of k over m would be more enlightening, wouldn't it? Sometimes I like to call this omega the natural frequency of the system. But when your mass and the spring constant are such that square root of k over m is equal to the frequency you're pushing it at, it builds up bigger and bigger oscillations, right? It's like on a swing. Every time it comes back, you push it forward. Every time it comes back, you push it forward. There's no resistance, right? There's no damping term here. And you get bigger and bigger oscillations. That's it. Or if you just push it randomly, sometimes when it's coming back, sometimes when it's coming forward, then you get this. All right. So we said those are the two cases. So what else is there to do? We got one more case actually. Case 3. It's not really a separate case. It's a special case of the first one. It's square root k over m is approximately equal to the frequency you're pushing it at, like the natural frequency it wants to vibrate at. If you had no resistance and no pushing force, it would just do simple sinusoidal motion with this angular frequency. If you push it at almost that same frequency, but not quite the same, you'd think you'd get something close to resonance, but not quite, right? How can that be? How do you resolve that these are so different all of a sudden? You say, well, if it's approximately but not equal, then what you get is you can combine these two. You get something between those two results. You get something that starts out looking like it's going to be resonance, but then it's not quite resonance. And that fact means you start pushing against the swing after a while, and it comes back down like this. But then it starts building up the resonance, and then it damps it back out. And it gets a motion like this, called the phenomenon of beats, where it actually oscillates up and down between a plus and minus a sine function. So you've got a beat, a beat, a beat. And I'll just illustrate that with an example. Rather than proving this, which we can do, it's a lot of abstract trigonometry. It's kind of boring. I think if you see the example, you'll see why it works. What you really want is these amplitudes to be about the same. And get the similar amplitudes on U particular and U homogeneous, and almost equal frequencies. Then you can start to notice this thing. If they're not almost equal amplitudes, yes, you'll get a little bit of this thing called the phenomenon of beat. That's the beats here, beat, beat. And so you get a tone, that's the sound, like on and off, on and off. That was the illustration that we did at the beginning last time that you couldn't hear. But hopefully you listened to it online since then. Both tuning forks are both making a noise, but the noise between them goes on and off, on and off. How is that? It's trigonometry, actually, that comes out of these differential equation solutions. So let me just do an example of the phenomenon of beats rather than proving it in generality, and you'll see why it works. Here's the example I put in the notes. It has some nice numbers, so I won't get too bogged down in those, hopefully. So I take d squared u dt squared plus 4u plus 17. No, I'm sorry, plus 4u equals 17 cosine 9t over 4. And I'm going to find the general solution of that. Solve this one. And what you'll find out is the two frequencies are not the same. It's the sum of sine waves. But because they're close in frequency, these jumbled sine waves together start to look like beats. So that's the resolution between how do these things mesh. As the frequencies get closer and closer together, you get longer and longer beats until you sort of just get one big beat here, point out to infinity. That's how they come together. So to solve this, what we do is we say, first consider the homogeneous problem, d squared UH dt squared plus 4UH equals 0. Gives me a characteristic equation r squared plus 4 equals 0. Because r is plus or minus 2i. Because of the homogeneous problem has general solution, an arbitrary constant times cosine 2t plus an arbitrary constant times sine 2t. And when you get pure imaginary numbers here, 0 plus or minus something times I, then you get just cosine and sine. Step 2 is to look for a particular solution, right? By undetermined coefficients, right? We just look in the table. Because this is not a solution to the homogeneous problem, right? It would be if this was cosine of 2t, right? Cosine of 2t would be a solution to the homogeneous problem. This isn't. This is cosine of 2.25t. So it's not going to be a solution to the homogeneous problem, but it's close, right? It's close to 2t. So by undetermined coefficients, we look for a solution. In particular, is a number times cosine 9t over 4 plus a number times sine 9t over 4. There will be a solution to this problem. The table of undetermined coefficients guarantees it. You plug that in to see what the numbers are, right? These are not arbitrary. The C1 and C2 are arbitrary. That's getting the general solutions. Initial conditions will determine those. These are specific numbers for a particular solution, one solution. And the table says there is one solution that has these some numbers here. We have to find out what they are. So we're going to plug this in. And what we get is the second derivative of that is, right, if you take the derivative of cosine twice, cosine 9/4 t twice, you get minus 9/4 squared cosine. So it's minus 9/4 squared cosine 9t over 4 is the second derivative of 9t over 4. And that's all multiplied gamma 0. Actually, and the second derivative of sine is minus 9/4 squared sine squared 9t over 4. There it is. This is the second derivative of UP. It's going really fast. So the cosine is minus 9/4 sine, and then take the root minus 9/4 sine, we get minus 9/4 squared cosine. That's what. All right. Now we want to add that. I'll put it in here, and then plus 4u. So u is just gamma 0 cosine plus delta 0 sine. And all that has to add up to what we see on the right-hand side, 17 cosine 9t over 4. And undetermined coefficients guarantees us there are some numbers, gamma 0, delta 0, for which this works. How do we solve this one? This might help you on the test. There won't be an applied problem, but you still might get a differential equation like this to solve, right? Because that's undetermined coefficients. We did this. So this is actually practice for the test on this one. The only reason it's in this section is it's supposed to be showing a model for the mass on the spring. If the spring constant was 4, this was the right-hand side. This is what you do. What I won't ask is I won't ask you all the stuff on the phenomenon of beats because that's in the application section, right? But I might ask you to solve an equation like that. So this part is good anyway. What we do is we group all the like terms, right? We'll subtract this over to get 0 on the right, just like we did in the other problems. But we'll group all the cosine 9/4 t terms. They multiply, let's see, minus gamma 0 times 81/16. So minus 81 gamma 0 over 16. And then I've got another cosine over here. Minus 16 gamma 0. Oh, times, yeah. Let's see, that's 16. It's 4 minus plus 4 of these, right? I'm sorry. Plus 4 gamma 0. Cosine 90 over 4. That's all the cosine terms of that one. Minus 17. All right, so put this over, and then there's 3 cosine terms. Then there's also some sine terms, right? There's sine 9t over 4 multiplying gamma 0. Oh, wait a minute, I got this mixed up. This is gamma 0 here. This is right. This is delta 0 here. Second derivative delta 0 sine. Squared on there. Minus gamma 094 squared cosine. Minus delta 094 squared sine. There it is. Try and talk and write some of the can't do it. All right. Okay, so minus 81/16 plus 4 minus 17. And then the signs are minus delta 0 times 81/4 plus 4 delta 0. And that's it. There's no more sign terms. All this is equal to 0. Well, how can this be equal to 0? For what values of gamma 0 and delta 0 will that be equal to 0? Anybody know? This is the trick. Because sine and cosine are linearly independent functions, this is equal to 0 if and only if the coefficients of each function are 0. That's the power of linear independence here. We can now say, because these are independent functions, this must be 0, and this must be 0. Otherwise, their linear combination here can't be equal to 0 on an interval. So we observe then that this coefficient is 0. Well, let's see. This is minus 81/16 gamma 0 plus 64/16 is minus 17/16. That's the combination. These two added together, right? Minus 64 or plus 64/16. Minus 81/16, minus 17/16, and then minus 17. I just multiply gamma 0. Minus 17. That's this one equals 0. And then this one says minus 81/4 plus wait a minute. I didn't do my fractions right? Oh, that's right. Okay. This should have been 16, so. Sorry about that. 9/4 squared. Okay. So minus 81/16 plus 64/16 make minus 17/16. Delta 0 equals 0. There's a clue over here. So those are the two equations to make the coefficients equal 0. Well, that's easy because this one just said now that delta 0 equals 0. We generally have a system of 2 linear equations to solve. This one, by adding 17 over, dividing by 17, you get minus 1/16 gamma 0 equals 1. Add 17 over, this was equal to 0. Add 17 over and divide by 17. Tells you that gamma 0 is minus 16. So these are the coefficients that have to go in here, the particular solution, to get a solution. And so what we have then is that U particular is gamma 0 cosine, that's minus 16 cosine times t over 4 plus 0 sine. So it's just this. In this case, one of the coefficients happened to be 0. So it made it nice. Now here's the general solution of the homogeneous problem. Here's a particular solution. We infer immediately, right, that the general solution of the non-homogeneous problem three is U equals homogeneous plus U particular is C1 cosine 2t plus C2 sine 2t minus 16 cosine 9t over 4. Now, if you apply some initial conditions, you can see what the beats actually are, right? C1 and C2 have to be determined by initial conditions. Any questions on this so far? Everybody? Turn the sound up, someone just a little down here, I forgot. Now suppose I also apply initial conditions. U of 0 equals 1 and U prime of 0 equals 1. We start at 1 unit pulled out the mass and set it at 1 unit per second velocity. What's going to happen to this? We can plug it in and it's kind of complicated. This will determine C1 and C2, right? And you get 1 for U is equal to C1 times cosine of 0 plus nothing, multiplying C2 because it's sine 0, minus 16 cosine of 0 here. And so you get the equation 1 equals C1 minus 16. Tells you that C1 is equal to 17. Now, if you apply U prime of t is equal to the derivative of this is 2 C1 minus 2 C1 sine t plus 2 C2 cosine 2t minus let's see 36 multiply 16 by 9 fourths and get 36 sine, and then derivative cosine is minus, so it's plus 36 sine 9t over 4. Just doing a quick derivative here. This is the derivative of this one. And then you say U prime of 0 equals 1 says that 1 equals this plug-in 0 is minus 2. The first term is 0 because it's sine 0 plus 2c2 cosine of 0 plus 36 sine of 0 is 0. So you just get c2 equals 1. 1/2. But 2c2 equals 1. Now I have my unique solution to the initial value problem. So the IVP initial value problem solution. And this one, plug in 17 and 1/2. That's what I got on there. Oh, I got minus. Got 0 on there. There's a typo. I think this one should be 0 here. Let's do this one. If I do this one, this will be easier. Suppose this is the initial condition. Then I'll get 0 here. That tells me C2 equals 0. Now my solution is U equals U homogeneous plus U particular is this one. with C1 equals 17 and C2 equals 0. So it's 17 cosine 2t plus 0 minus 16 cosine 9t over 4. There it is. Okay. So it's the sum of two sine waves, right? One of angular frequency 2, one of angular frequency 9/4. 2.25. So they're close. This means it's actually sum of two sine waves, but they can be rewritten with the phenomenon of beats. Now, use the sum of the product formula. From trigonometry. Sum of the product formula says that cosine or difference to product, we might call it that. Cosine of alpha, maybe you remember this, minus cosine theta is equal to 2 sine alpha plus beta over 2 sine of alpha sine of beta minus alpha over 2. So you rewrite this and say that u, but the difference of cosines. Let me rewrite this a little bit. Let me call this cosine 2t. This is the way you prefer to write it, but for doing the phenomenon of beats, you break it up into two parts. You got a cosine here plus 16 times cosine 2t minus cosine 9/4 t. All right, so I'll just pull one of those cosines out. And now what I have is an amplitude multiplying a difference of cosine, and this will produce the phenomenon of beats. Same amplitude on these two. So this is the leftover part, and this is the phenomenon of beats. So you have a little wave plus beats. U is now equal to the first term, cosine 2t. It doesn't contribute to the beats. Plus the second term is 16 times, and we rewrite this 2 sine, and we add these 2 plus 9/4 over 2t. Well, so 2t plus 9/4 t. Make it clear what we're doing. Times sine 9/4 t minus 2t all over 2. Now what we have is cosine 2t plus 32 sine of, let's see, this is 17/4 over 2 is 17/8 t. And this one is 9/4 minus 2 is 1/4 over 2 is 1/8 t. So we've rewritten the sum of cosines or sum of sine waves as a product of sines, and this causes the beats because it's a sine times a sine. Now what you have is the lower frequency, right? The 1/8 frequency has period 2 pi over 8. So from 0 to 2 pi over 8 is pi over 4. This one completes one period. It's the lower frequency. And it looks like it has, with amplitude 32, this is the graph of 32 sine t over 8. Angular frequency 1/8. What does the product of these two look like? And then we're going to add it to this little cosine wave. Well, this just oscillates up and down between plus and minus 1, right? So it multiplies that wave by plus and minus 1. but it completes 17, it goes 17 times as fast, so it completes 17 periods for every time this one completes one period. What you then have is oscillation between plus this and minus this. Here's minus 32 sine p over a. And the actual beats there is done by something that goes up and down many times, 17 times, like that. And it just keeps going. There's another beat. And you notice there's actually 2 beats per period, right? There's a beat and a beat when the sine wave completes one period. So the beat period is not this pi over 4, but half of it. It's pi over 8. 1/2 period 2 pi over 8 of the longer wavelength here. And then what's this one? This is the average frequency. And so what you get is average frequency, angular frequency as opposed to frequency, of 17/8. And you divide that by 2 pi, you get the frequency. Frequency 17 over 16 pi. You divide by 2 pi to convert between frequency and angular. But this would be the hertz cycles per second that you'd hear, and you can see if this was in your hearing range. If you could hear this tone right here, which is halfway between the 2 frequencies of the mass, the frequency of the mass of the homogeneous solution and the frequency of the particular solution, this is halfway between the 2 frequencies. It's the sound you hear from the 2 tuning forks, but it's going off with this beat frequency, half the period of the other sine wave. That's the phenomenon of beats. And then there's this little cosine added on. So to this, you add a little something that's right. This is 32 units tall. You add a little 1 unit tall thing that wiggles up and down around that. I can't even draw it, but it kind of wiggles around that. But we can almost ignore that. But if you don't have 2 waves of the same amplitude, then you get this extraneous term that doesn't contribute to the beat. Any questions at all? That's kind of complicated, but I gave you one problem to figure out the phenomenon of beats, and you do this. Okay, it's trigonometry, but it's complicated. Hard trigonometry that you couldn't do at the time, even though you saw these sum of product formulas, product of sum formulas. All right, one last case because I've already talked too long on these. Case 4, we'll do this quickly, is the damped and driven motion. Everything on there, the damper and the driving force. That's what I call it, F drive. Damped driven motion. Damped force motion. And so, well, again, we'll just stick to the interesting case. Let's do a sinusoidal driving force. By the way, you'll notice that there's sections of electronic circuits. Ignore those. I don't want to take time for them. For electronics engineers, those should be of interest, though. And next week, when we come back, having done the problems on the mass and the spring, I'll mention the other ones. They're exactly the same thing, just with different numbers. I'll just mention them in passing as another application. So don't worry about this. Forget all the circuit stuff. All right. So now what we have is U double prime times M plus C times U prime plus K times U equals a number times cosine omega naught t plus a number times sine omega naught t. So this is a sinusoidal driving force of trigonometry. You could write this as a single sine wave. What are we going to do with that? Right? It's the last case. What you do is you solve the homogeneous part. And what's the solution? Remember this one? Associated homogeneous equation is just the one we did before, the undriven damped oscillator, right? And that broke up into three cases. It can be the underdamped case, the critically damped case. So the homogeneous solution we've already solved. It was the undriven oscillator. For the overdamped case, there's three cases you can get for the homogeneous part. Don't let that scare you. We already did it, right? Now you find a particular solution. Undetermined coefficient says there's a particular solution of the same form, right? Because it won't be a solution of the homogeneous problem. U particular is then let's say gamma 0 cosine omega 0 t plus delta 0 sine omega 0 t. And you plug it in to find those coefficients. They're not arbitrary. Just like we did in the last time we plugged in to get the coefficients, right? Once you plug them in, what you get is that U equals the sum of those. And it breaks up into these three cases. This one, by the way, is what? This is a sine wave, right? You can rewrite this as A0 sine omega 0 t plus B0. And so what you get is a sine wave plus one of these three cases. So you get a damped oscillator. For the homogeneous part, so UH is one of these, plus a sine wave for UP. And so the object here is have a feeling for what these things look like. You can already solve them. We did that last section, right? But what does it mean? You get one of these three cases plus this case. So let me see if I can just put it up on the board from the computer. I think that'll be better. There we go. This is what happens. Before, we could have a like in the underdamped case, this would be underdamped motion, right? If we had no driving force, but we were underdamping our shock absorbers, the car would bounce up and down, and it would settle down as equilibrium position. That's the homogeneous solution here. Now add to that the particular solution, because we're actually driving at this time. Looks like this. It's a sine wave, right? That's the particular solution. What happens when you add these two, the red and the magenta? Well, you stack the y coordinates, this one plus this one. Initially, this one overpowers, but this one damps out, and in the end, what you settle down to is the particular solution, this is the sine wave. Consequently, since you settle down to the particular solution, we say the particular solution is the steady state term, and the homogeneous term that damps out, we call the transient term. Well, I'll let you draw that picture because I can't draw it on the board. I'll fumble. But what happens is that we call this the homogeneous term is always called the transient term because it damps out. Whether it's underdamped like we showed on the overhead there, or critically damped or overdamped, it doesn't matter. It damps out. And then this one is the steady state term, because when you add something that damps out to something that doesn't, one of the things that doesn't, we call steady state. When you hear those things in your engineering or physics class, that's what they're referring to. You got a sine wave that it settles down to. That's the steady state term. What damps out is the transient term. We're all done. I'll let you try some examples and bring some questions next week. Maybe we'll do one of these on Monday, rather than actually try to do an example on this. See if you can. All it is solve the coefficients and note it and pick out which term comes from homogeneous, which one comes from particular solution. So solving same problems as before, just having this interpretation on it. Well, let's see what can we do for today then. Review. Any problems that are getting in trouble, again, I'll go sit in my office after class for a while if you have any more questions.
Could you do number 8 from the review?
Yeah. Sorry, I meant to leave more time. So suppose I have y triple prime plus y prime equals 2t plus 3. How about that? You know what? I'm going to leave that off. Let's keep this test to second order equation. This is the third order. I think I said I'd only do through second order. So let's omit that one. Only do second order on this test. We'll do this one next time. Didn't really talk about this one. Sorry about that. I forgot to. I didn't get to those. Anything else? Good question. This one? 10. Okay, let's look at 10. Solve a non-homogeneous differential equation t y double prime plus 2 plus 2t y prime plus 2y equals 8 e to the 2t by reduction of order, given that y of t is 1 over t, is one solution of the homogeneous problem. This is a trick problem. If you got stuck on it, it might be for this reason. There's a formula, right, that I gave you for the reduction of order. Said by reduction of order. That formula only applies if you put it into standard form. This is not in standard form. So if you plug this into the formula, it'll come out wrong and say, what happened? All right, so the first thing you do is put it into the standard form. You divide through by t and write y double prime on an interval where t equals 0. These are equivalent. Okay. I'll put it in the standard form, and then I'll say, and then I can apply the formula. Or, in lieu of the formula, we said, all you really have to do, so you don't have to memorize that formula, you know, in the workplace, you don't want to look it up. But it's not too hard to look up these days with the internet, but it's to write y equals dy1 and substitute it in. It's the same method we used for the homogeneous case. Just in the non-homogeneous case, if we keep all the arbitrary constants, we get the general solution. So if you leave the constants out as you integrate, you'll get a solution, and then you can solve the homogeneous problem. But if you want a non-homogeneous one, you leave the constants in. So this is equal to, with y1 equal 1 over t, this is equal to v over t. So y prime is now the derivative of that is d prime over t minus d over t squared, right? Derivative of 1 over t is minus 1 over t squared. And then y double prime is the derivative of this, b double prime over t. Again, I have to use a product rule or quotient rule. Product rule is easier. Think of b times 1 over t. So it's first times derivative of the second plus, sorry, derivative of first times the second plus first times derivative of the second is then minus b prime over t squared. And then this one has a product rule too. Think of it as b times 1 over t squared. Get minus b prime over t squared plus 2b over t cubed. So this is the product rule applied to this one. Derivative minus 1 over t squared is minus 2 over t cubed. Derivative t to the minus 2 is minus 2t to the minus 3. So I need to plug all those into the differential equation. Plug in to get, well, let's see. This one I need if I do the formula, all right? But if I'm not going to use the formula, I can leave this off. So let's say if I don't use the formula, then I get t times y double prime, and I plug that in. These can be combined. This is b double prime over t minus 2 b prime over t squared minus 2b over t cubed. Wait a minute. I should have put a minus here. I put both of these together and I forgot. So this is plus, right? Yeah, that should have been minus. This is plus. Took the derivative of this one, included the minus by mistake. Okay. So I get that, and I put that in here. B double prime over t minus 2 b prime over t squared plus 2b cubed. And then that's multiplied by t plus 2 plus 2t times y prime is this one, b prime over t minus b over t squared. And then plus 2y, plus 2 times y is b over t. All equals 0. Now when we're talking, oh, not equals 0, equals 8 e to the t. This is not homogeneous. 8 e to the 2t. All right, question so far. Reduction of order, whether it's homogeneous or not, you substitute y equals b times the solution you know, in this case 1 over t. Take the two derivatives, plug them in. What happens next in reduction of order? Sure. You did it right, all the terms where there's just v, not v prime or v double prime, they cancel. So this one, and this one should all cancel. Let's see. 2t over b cubed times this is 2b over t squared. Let's see. Cancels minus 2b over t squared. That one goes. That one and that one goes away. This one times this one goes away. And then this one, 2b over t, and this one is also minus 2 over v, they cancel. So this one, all cancel. All the v terms fall out. This times this cancels this one, this times this cancels this one. That's what you look for, is all the v's go away. That's reduction of order, gets rid of the v's. Now what I have is this times this is v double prime, nice, minus 2v prime over t squared. And then over here, plus 2v prime over, plus 2 over t, take this times this, 2 over t plus 2 v prime, all equals 8 e to the 2t. That's what I have left. So I divided this one by t to get this. The idea of reduction of order is now I substitute w equals d prime. So the w prime is dw prime, is d double prime, and it reduces the order. I get w prime minus 2w over, oh, I need to combine these. Let's combine these first. Minus 2v prime over t squared, so this is d double prime plus something times v prime equals 8 e to the 2t.
Shouldn't it be 2 minus 2v prime over t, not t squared, for the second term you have? No, down a line. Right there.
Yeah, this is supposed to be a t. Yeah, thank you. And this is nice because now this one's going to cancel this one, right? Minus 2v prime over t plus 2v prime over t. That's coincidental. I don't know what's happened. Now what I have is plus 2v prime. There's the differential equation I'm left with. Thank you. Now I substitute that and I've got w prime plus 2w equals 8 e to the 2t. Here's what always happens next. You started with a linear equation, and when you make the substitution, you always get a linear equation. But now it's first order, so it's a first order linear equation. You have a formula for that, right? You can take mu equals e to the integral p of t dt is integral 2 dt, right? Coming from here, p of t equals e to the 2t. So if I multiply this through by e to the 2t, I can integrate this. The left side will be a product, or I go right straight to the formula, right? Y equals 1 over mu. I use this one so much, I just memorize it. Integral mu f dt. Right? So many other methods reduce to first order that I have to memorize this one. I spend too much time doing the other way. All right, so 1 over mu would be e to the minus 2t, and I don't need to put my plus c on here because you just want any integrating constant will make this work. You don't have to have all of them. It's supposed to be e to the minus 2t is 1 over e to the 2t times the integral of mu, which is e to the plus 2t, f, which is 8 e to the 2t, dt. Plus here, right? And now we've got e to the minus 8 e to the minus 2t times the integral e to the 2t, e to the 2t is e to the 4t, right? Integral e to the 4t is easy, it's e to the 4t over 4. Put it down here. Plus an arbitrary constant. This one you do have to keep, or you won't get all solutions. Call it C1. And we've got, let's see, these two partly cancel, and these two partly cancel. We get 2 e to the 2t plus this one, 8c1 e to the minus 2t. There it is. That's not y though, it's v, right? V is what we were solving for, or w. I'm solving this equation for w. Now I'm going to have to erase something else here. Now v is the integral of w, remember, because w is v prime. Is the integral of 2 e to the 2t plus 8c1 e to the minus 2t dt. If I integrate term by term and I get e to the 2t minus 4c1 e to the minus 2t. Integral of e to the minus 2t is e to the minus 2t over minus 2. I got that. Plus, we need this arbitrary constant to get all solutions. Kind of the double check that you get when you teach this for a while, and you're solving a second order differential equation, you ought to get two arbitrary constants. Ah, there we go, we got them. Now, finally, that's b. So y is equal to v times y1, recall. V is this one, e to the 2t minus 4c1 e to the minus 2t plus c2 times 1 over t was y1. Evidently, I've got e to the 2t over t minus, let's call this, let's call minus 4c1, whatever, c1 hat. And we could call this one c2 hat. C1 is an arbitrary constant, minus 4c1 is an arbitrary constant, right? So we'll call this plus c1 e to the minus 2t, c1 hat e to the minus 2t, plus c2 hat is the same as c2, all over t. So there's the general solution of that differential equation. Hopefully that looks like the answer. Yeah, okay. Tricky, huh? That's a good one to do because that's probably one that you all tried last, right? Anything else you want to look at today?
Could you do number 6 from the review?
Okay. For the test, I may not just ask a few problems, I can ask anything similar to the homework. So probably most of them will be based on the review, but there might be some based on homework. If you have any homework questions, you can ask those too. Here's number 6. Solve y double prime minus 1 over t y prime plus 5 over t squared y equals 0, together with the initial conditions, y of 1 equals 1, y prime of 1 equals minus 1. What kind of equation is this? That's the trick, is that it's sort of like a cookbook. If I'm baking a pie, I get this stuff out. If I'm baking bread, I get that stuff out. What am I baking here? 14 not equal to 0. You can multiply this through by t squared and write this as t squared y double prime minus ty prime plus 5y equals 0. It's what kind of equation now? Euler equation, right? Has a longer name too, Euler something equation. Cauchy-Euler equation. You see that term, it's the same thing, Cauchy-Euler. The way we solve these is there's a characteristic equation for an Euler equation, right? You write, here's A, here's B is minus 1, and here's C is 5. You write A times R minus 1 plus B times R plus C equals 0 is the characteristic equation for an Euler equation. Is now 1 times R minus 1 minus 1 times R plus 5 equals 0. That's the Euler characteristic equation. It's always a quadratic equation once you multiply it out. Okay, it's r squared minus r minus 2r plus 5 equals 0. And so we solve that and we fail trying to factor it. Why do we fail trying to factor it? So it does factor, of course, right over the complex numbers. Anything factors over the complex numbers. But it fails over the real numbers. This is imaginary. It's better to use the quadratic formula. R1, R2 minus B is minus 2 is plus, minus 2 is plus 2, plus or minus square root B squared minus 4 times A times C all over 2A. And let's see, we've got 2 plus or minus square root of minus 16 is 4I. Oh, they're coming out nice. I must be doing it right. 1 plus or minus 2I are the solutions to the characteristic equation. Now you memorize the form of the results for those. Two independent solutions are, you call this alpha plus or minus beta I. Two independent solutions are t to the alpha cosine, when you have imaginary ones, cosine beta ln t, and t to the alpha sine beta ln t. You can memorize that or look it up. But those are the two independent solutions in the complex Euler case. They gave you a hard one there, didn't I? Those are the independent solutions. So what we have is y equals c1 times the first solution plus c2 times the second solution, where alpha is this and beta is this. So it's t times cosine 2 natural log t, and t to the 1 sine 2 natural log t. There's the general solution, just like that. One goes here, here. And if you want to solve it on t less than 0, then you have to put absolute values on everything. You want to put it here. Now it's good for t greater than 0 or t less than 0. Or before, you put absolute values on these two. So if t is greater than 0, you can drop the absolute values. And these can be taken off if you're multiplying by arbitrary constants, plus or minus anyway. But the ones on the outline have. Okay. Hopefully that looks like you want the answers back. That's what I wrote in there without the absolute values. I won't worry about the t less than 0 case on the test. I just want you to know that in case you run into it at work. Don't know absolute value and fix it. Any other things you want to look at?
Question 4.
Okay. We're running around of time in 1 minute, so if you have to go, go ahead. And otherwise, I'll just finish this for everybody who stays on. Question 4 says this, t squared minus 2t minus 15. I'm glad you asked this. I wanted to do one of these. Y double prime. This won't take too long, actually. Plus natural log t, absolute value t, y prime minus y equals t squared, together with initial values, y of minus 2 is 0, y prime of minus 2, 1. Find the interval on which this initial value problem is certain to have a unique twice differentiable solution. So find interval for unique solution. Twice differentiable assumed. So you take the derivatives. This is a linear equation, right? It's y double prime plus p of t, y prime plus q of t, y, with continuous functions for y greater than where these are continuous, you can apply the theorem. But the point is, it's a linear equation, so I can use the nicer theorem for linear second order equation. But what you have to do is put it in the standard form first, right? In order to check the existing uniqueness, you say standard form is y double prime plus ln t natural value over t squared minus 2t minus 15 y prime minus y over t squared minus 2t 15 equals t squared over t squared minus 2t. All right. And now this is tricky, actually. Call this, I can't call this P and Q yet. I didn't put standard form. This is P. And this is Q. This is, that's a Y here. And this is F. Where P, Q, and F are continuous, you get a unique solution. You might get one on a longer interval, but the theorem guarantees you where these are continuous, you get a unique solution. So you can't include t equals 0 because natural log is not continuous there. So this is going to be all t except what? T equals 0 because the logarithm fails to be continuous. Where else do these fail to be continuous? Where the denominator is 0, right? So you factor this as t minus 5, t plus 3, right? T squared minus 2t minus 15 is this. So it also fails to be continuous at t equals negative 3, t equals plus 5. It will be continuous. It will have a unique continuous solution on any interval that doesn't include these and does include the initial value t0 equals minus 2. So the trick here is to include the initial point exclude the points where those are not continuous, 0, minus 3, and 5. What's the biggest interval I can make of the t-axis that excludes minus 3, excludes 0, excludes 5, but includes minus 2. Oh, there it is. Easier to visualize this sometimes. It's t between negative 3 and 0. That's how you do those. You look for where are these, you put it in standard form, ask where are these continuous. That's it. Thank you, Aston. Thank you. Any other burning questions? If anybody wants to stay there, we have a few minutes. There's another class coming in there. We're only a minute late, aren't we? But there's another class at 11, but I'm staying in this room till close to then I'll go over to my office. If it's still up to me, I'll meet you there. Anything else?
Did you do 2A from 3.2.1?
Yeah. Close my stuff. Where is it? I'll get it back up. Sometimes I close these things without thinking. Okay. Okay, 2A says this. Will I have m d squared r dt squared equals minus g m m over r squared is my differential equation. And reduce this to first order by multiplying by integrating factored by y prime. Reducing order. This is the energy method. I have all those letters in there, G, M, M, M. I've seen gravity before, right? Mass times acceleration equals, this is Newton's law for gravity, minus gravitational constant times the mass of the big thing, like the sun, times the mass of the little thing, the earth or whatever, over r squared. This is the gravitational force law, right? The radial component of it. And what you can do, oh, I said multiply by y prime, then that should be r prime. Oh, I said if it's of the form y double prime. I should have done this one, said r prime. So multiply by r prime on this one, since r is the integral. So I divide through by m, that might help me. This is equivalently d squared r dt squared equals alpha times 1 over r squared, where alpha is minus gm. I divide through by m, I can cancel those. So that's the simplified equation. There's really only one arbitrary constant in there, p times m. This is mass times acceleration equals force is the idea though. Now I multiply by r prime, and I get dr dt times d squared r dt squared equals alpha 1 over r squared dr dt. And then I integrate. You multiply by dr dt and integrate. Put the constant alpha outside. What do I do with this one? It's a u substitution, right? dr dt is equal to dr. It's an r substitution. Alpha times integral 1 over r squared dr by the substitution rule. And then this one, what's this one? You just kind of memorize this, but you can figure it out by the same thing. You can write this as, if you like, you can use r substitution again. Say this is integral dr prime dt dr. Let's just write it this way. Comes out to be 1/2 r prime squared. You take the derivative of it, 1/2 dr dt squared. Let's write it the same. The derivative of this, if you take it, is this by the chain. So it's 1/2 v squared always when you do that. So now what you've got is dr dt equals plus or minus square root of 2 alpha integral 1 over r squared dr is plus or minus square root, alpha is gm, so 2 gm integral 1 over r squared is minus 1 over r plus a constant. Except, I forgot my minus here. This should alpha equals minus gm. Right? And so this is minus 2 gm. And I get 2 gm over r squared over r. I'm integrating that one to minus r plus a constant. Comes out to what that comes out to be, right? Integral 1 over r squared is minus 1 over r, and then times the minus 2 gm is that minus 2 plus 2 gm over r. Then there's the integration constant. C times 2 alpha is still an arbitrary constant. In gravity, this constant comes out to be 0, and you just get this actually. But, We reduce it to a first order equation. Stop. All I asked for. Oh, I said that, no, I said solve the first order problem, didn't I? If you assume, I should put this on there. Assume that r prime goes to 0 as r goes to infinity for gravity. Gravity goes to 0 as you go to infinity. Tells you that c equals 0 in here. Now what you've got is the r dt plus or minus square root 2 gm times 1 over square root r. Next class is coming in. Then you can integrate that and get r is the integral of that. Multiply by square root r minus square root r dr is equal plus or minus square root 2 gm dt, separate variables. And now you've got r to the 3 halves, 2/3, r to the 3 halves over 3 halves, equal plus or minus square root 2 gm t plus a constant, which is your initial position. And so you get this kind of a solution. I'd say that's implicit solution. This is the 3 halves law, the radius force on 3 halves times the time power out of Kepler's law. All right, so I'll leave that there and say that's as far as I want you to go on that one. Thank you for coming in. Come over to my office hours if you want. I'll meet you there.